In ecological systems, interactions between various species like mice and owls depend on a complex web of interactions that are usually difficult to grasp directly. We can often get a hold of them by describing the rate of change of each quantity involved based on the influence of the others, which allows us to create models of what is going on in these environments. I'm Bernhard Werner, this is Sum and Product, and in this video I will give an introduction to differential equations and how they can be used to model phenomena in nature. In general, a function f from a to b describes any assignment of elements of the set A to elements of the set B. For example, the assignment of a car model to the set of possible rims, of a sport to the number of players per team, or of a set of apples with a certain weight to their price. In the last example, people have a fairly precise idea of how the price of apples should behave. The price p as a function of the mass m should grow linearly. If the apples weigh twice as much, they should also cost twice as much. There should therefore be a relationship of the form p equals alpha times m, where alpha is a number that indicates the price per mass. However, many functional relationships are difficult or even impossible to describe directly, but they can often be described by how the function changes, by how quickly it rises and falls if you move along the input variable. Equations that describe such changes are called differential equations. The word differential here comes from difference and describes exactly this change we are interested in. Much more concretely though, it means that it is an equation that contains the derivative of the function. The derivative f prime of a function f describes exactly this rate of change of the function at any given point. We can calculate it by approximating the function at the point of interest with a line. It runs through the point itself and another point further down the function graph. For this line, we can calculate its slope via the usual rise over run expression. If you let the second point approach the first one, the line slowly becomes the tangent at the function graph, and the whole process is described as the limit of the rise over run calculation. Now, the slope of the tangent is exactly the rate of change of the underlying function itself. It is not possible to define this for any function though. For example, this one here has a graph with a sharp corner, so the tangent isn't unique there and the slope isn't well defined. But whenever the graph of the function forms a smooth curve, it works. If you have never seen this, you might wonder whether this derivative can be calculated for arbitrary smooth functions given a function term. A common way to go about this is to start with the simple example of f of x equal x squared. Calculating the rise over run for the approximating line via the binomial theorem gives us the term 2x plus h. And since we let h become 0 in the limit, the rate of change of f at a point x is 2x. With similar calculations, you can find the derivative of all integer powers of x. Then you would proceed to analyze other basic functions, for example sine and cosine. Depending on which definition you use for the trigonometric functions, this might be rather cumbersome or blatantly obvious. After building a small dictionary of derivatives this way, the key insight is that there are general rules about how the derivative behaves if two functions are combined. For example, if they are added or multiplied together, we can describe the derivative of the result based on the derivative of the original functions. The most interesting rule is the chain rule that describes what happens when a result of one function is used as the input for another. These rules allow us to break complex functions into smaller parts and calculate the derivative step by step. With them, we can calculate derivatives of so-called elementary functions, basically the examples you see on screen and everything you can build by combining them. These rules also help in analyzing general statements about derivatives, which are important for the study of differential equations, like the ones we will now look at. In general, derivatives make it possible to describe dynamic processes based on the change of a certain quantity instead of having to determine the value of the quantity directly. And real-world applications often revolve around processes that can be described as some form of growth, which will be the focus of the rest of this video. One particular function that is incredibly important to modeling phenomena in nature is the exponential function. Its main feature is that it is its own derivative. Similar as to sine and cosine, it depends on the definition you use whether this is easy to prove. A common definition is via this infinite series. Using the rules for derivatives we already saw, you can show that calculating f prime here gives you f again. With more effort, you can show that any function, which is its own derivative, must look like this. For now, we will take it as a given fact. Exponential growth now is one of the simplest models for a growth process. Although it very rarely occurs in pure form in nature, it forms the basis for many others. Consider a species of bacteria. We assume that each individual reproduces independently of the others. Reproduction takes place after a fixed period of time for each individuum. There is enough space and resources and no predators or other dangers so that reproduction can always continue in this way. These assumptions aren't realistic, of course, but you can imagine the bacteria in a nutrient solution, in an enormous container. So not necessarily a scenario found in nature, but maybe in a lab. We can now ask how the bacteria will grow under these assumptions. As the individuals reproduce independently of each other, there's a certain number alpha that describes how many offspring a bacterium produces per unit of time. We can simulate it with, say, a growth rate of 0.5 bacteria per second. That means each bacterium produces an offspring on average after 2 seconds. We get something like this. Because we can't actually let the simulation, or real bacteria for that matter, grow indefinitely, we'll just stop at some point. As this number alpha is the same for all individuals, this means that the rate at which the number of bacteria changes, its derivative, is proportional to the number itself, with alpha as the proportionality factor. The solution to this equation is given by n equal to n0 times e to the alpha t. n0 describes the number of bacteria at the start. There are strategies to find solutions to these kind of equations. In this base case, however, pretty much always boils down to just knowing that the exponential function is its own derivative. And this here is the very, very basic way of doing mathematical modeling, making some assumptions about the situation that can be observed, formulating them in equations, often involving the rate of change of quantities, and then trying to solve the equations. At the end, of course, we have to compare our solution with the real-world data we started from. In nature, exponential growth never really occurs, as there can obviously be no growth process that goes on indefinitely, producing arbitrarily large numbers of individuals. Experiments, such as those on bacterial growth, show that an initially exponential phase is usually followed by a leveling off in population numbers. These S-shaped curves contradict the assumption that individuals reproduce independently of each other and are therefore much more realistic. Growth is slower when more individuals are present. Depending on the scenario in question, there might be various reasons for that. Hares in a forest only have a limited amount of food. Birds in the same forest might fly outside for food, but only have a limited number of nesting sites within the forest. In all cases, the population size n approaches an upper population limit n max, and the closer it gets to this limit, the slower the population increases. In contrast to exponential growth, the derivative of the population number n is now not only proportional to the number n itself, but also to n max minus n, to reflect this competition for resources. Together with a proportionality factor alpha, which is again intended to describe the growth rate, the differential equation of this process is just this here. The solution to this is now much more complicated, but it is still straightforward to check that the derivative of this function n really is proportional to n times n max minus n. We call this a logistic function, and the process is also known as logistic growth. The name probably comes from the Greek logistikos, and was introduced by Pierre-François Verhulst in 1847. However, the reasons for the choice of this term are not known as far as I'm aware. In the real world, both the growth rate alpha and the upper bound n max depend on a wide variety of influences, like the amount of food and number of nesting opportunities mentioned above. As the differential equation itself is quite simple, and the actual influencing factors are hidden in the constants alpha and n max, this equation can be used for many processes in which some kind of saturation occurs. For example, chemical reactions, the spreading of a disease, or even how new words and phrases are adopted in a language. One feature of this type of growth process is that it looks like exponential growth at the beginning. Here, at the beginning means a point in which the actual population number is much smaller than the upper limit n max. It would make intuitive sense too. If there are plenty of resources available, the population can grow just as if there were infinite resources. To analyze this, we assume that this point in time is at the start when t is 0 or very close to it. That means we assume that n0 is much smaller than n max, which we denote with this double smaller symbol. For the factors in the numerator, this doesn't say much, since a small number times a large number can be anything. But in the denominator, we subtract them from each other at the end. Because we assume that n0 is much smaller, we can approximate it with 0 in this comparative case. Next, the exponential factor is very close to 1, since we assume that t is very close to 0. That means the second summand in the denominator is close to n max, and we add n0 to it. With the same argument as before, n0 being negligible, we can set it to 0 again. With a bit of rearrangement, we get that logistic growth really does behave like exponential growth if n0 is much smaller than n max when t is 0. Not only does this show that logistic growth is an adequate generalization of exponential growth, it also justifies using exponential growth as a simplified model if it's only just starting out, as is for example often done when modeling the spreading of diseases. In the previous section on logistic growth, we assumed that the habitat itself is essentially constant, and that reproduction is therefore only dependent on the population number. In nature, of course, the population of a species interacts with the environment in many intricate ways. Probably most notably are the interactions with other species. We now want to look at a model where exactly two species interact with each other and everything else in the shared environment remains unchanged. It is therefore again a model that only approximates the real situation in an ecosystem. The first species represents prey animals, for example mice, and we denote the number over time by x of t. This species should be able to feed itself from the resources available in the habitat. The second species consists of predators, such as owls, which only eat the first species and need them to survive. Its population is denoted by y of t. Furthermore, in contrast to logistic growth, we will ignore competition within the species here. Let alpha be the reproduction rate of the prey animal. Just as in the previous sections, x prime must then grow as alpha x grows. The more individuals there are, the more individuals are born. However, the number of individuals in the prey population must also decrease the more predators there are. To be more precise, the number x times y describes the number of opportunities for a predator to encounter a prey animal. Let beta be the probability that such an encounter actually happens and leads to the successful catch of the prey animal. Then the prey population must decrease by beta times x times y. Note that all of these quantities refer to the population number at a specific but arbitrary point in time t, but we usually drop the of t part from every function to make it easier to read. For the predators, we can make similar arguments. They die out based on a mortality rate of gamma. The change in the number y prime must therefore fall with gamma y, so it gets a minus sign. They can also reproduce if they can catch enough prey. The number of opportunities to do so is again x times y. Let delta describe how many predators are born on average per prey animal caught. That obviously does not make any sense for an individual predator. But if you look at the whole of both populations, the ratio of predator animals born to prey animals caught will be roughly constant. This results in a system of coupled differential equations, in which several variables influence each other. These equations are referred to as the Lotka-Volterra equations, as Alfred Lotka and Vito Volterra described and analyzed them independently of each other at the beginning of the 20th century. How these equations can be interpreted in the context of two populations in nature is discussed in the so-called Lotka-Volterra rules we will see soon. Before we do so, let's look at these differential equations themselves. One of the first interesting questions about such systems is whether there are stationary solutions. In other words, is it possible for the numbers x and y to be constant over time? For constant functions, the rate of change is 0. That means a necessary condition for this situation is that the right-hand sides of our equations here must be 0. We can factor out an x and a y respectively. We get a first case in which both populations are 0. While that is actually realistic, the habitat we are looking at could simply not contain any of the animals we want to study, it is not very intriguing. So let's consider the second case. Here, the second factors must be 0. This means that x must be equal to gamma over delta and y equal to alpha over beta. If the number of predators is just right, it offsets the birth rate of the prey animals exactly to keep the rate of change at 0, and vice versa. The fact that a stable predator population depends on alpha and beta, but a stable prey population doesn't, can be observed in nature. For example, when people try to help phytoplankton by adding iron salts to the ocean, the plankton population increased shortly afterwards. But in the long run, the plankton population went back down and only the animals that fed on the plankton had a higher baseline number. These kinds of perfect equilibrium points never occur in nature, of course. There, we will always have some sort of fluctuation. Let's look at how these fluctuations look like. Actually look, in this case, since an explicit solution to these equations cannot be calculated. But what we can do to get a sense of what's going on is to draw a so-called phase portrait. Take this coordinate system. As a bit of foreshadowing, I named the population numbers of the two species x and y. So that is what we will do. For any point in this coordinate system, we interpret the x-coordinate as the number of prey animals and the y-coordinate as the number of predators, both for the same given point in time. For example, this point here would represent a situation in which there are 200 prey animals and 50 predators. Our differential equations now exactly tell us how both population numbers and therefore coordinates change. Here in this geometric view, this is just the velocity, the direction and magnitude with which the point changes its position over time. That means we can draw it as an arrow attached to the point to indicate how both populations would evolve from here. Now we do this for every point in the coordinate system. Well, not every point, of course, just a lot. Moreover, the velocity vectors are often way too long to create a useful picture, so it's a typical practice to scale them down by a common factor to make it easier to see what's going on. This is the so-called phase portrait of our system of differential equations. It gives us a qualitative description of how the system changes over time. Even if you just take this as a static image, you can probably see that a set of population numbers will move counterclockwise around a center, which is the stable solution we talked about earlier. But since this is an animation that I coded, we can let the marked point fly around the phase portrait by making it follow its velocity vector. And it will stay on a fixed orbit around the central point. In fact, wherever you start, the populations will stay on such a closed trajectory. More concretely, you can describe these curves by the expression on screen. On every orbit, it will be constant. For the one shown, it might be 4. For a trajectory closer to the center point, it might be 100. But as long as the population point follows the velocity given by our differential equations precisely, this value won't change. You can find this expression, by the way, by dividing the given differential equations to directly relate how y changes dependent on x. Then you use something called separation of variables, which is one of many techniques to massage or even solve differential equations. Instead of going into details here, however, we now want to look at these equations in a real-world context. As mentioned already, when we discussed the equilibrium point, things aren't that neat in practice. To describe how these differential equations correspond to more concrete rules in an ecological setting, let's do a quick simulation. Here we have blue icons representing prey animals and orange icons representing predators. For the parameters, we simulate alpha and gamma directly. We let every blue mouse spawn another one in a random direction at a fixed rate. And we let an orange owl vanish with a given probability. Now to their interaction. The naive approach is to let an owl catch a mouse when their icons touch, which does work, but the result is fairly unstable. In particular, the owls often caught all the mice if the latter were trapped in a corner of their habitat. So I decided to let the computer roll a die whenever an owl gets close to a mouse. And depending on the outcome, I count it as a catch. Not only does this make the simulation more stable, as the mice are not that easily overpowered, it is also more in the spirit of what the parameter beta is actually modeling. When it comes to new owls being born, there are two approaches. We can let each owl keep track of how many mice it caught and spawn a new owl once this reaches a certain threshold. Or we simply let an appropriate proportion of those owls, which just caught a mouse, spawn an offspring. I didn't see much difference in my experiments, and so I take the second option as it is easier to debug. Now, we increase the number of both populations and let the simulation run. Every animal goes off in a random direction, and on the border of the habitat, they simply bounce in a random direction inwards. We keep track of the population numbers and also the position in the phase portrait. The latter tells us that our simulation is at least somewhat realistic, even if it's fairly wonky. The former lets us observe the Lotka-Volterra rules. First, the predator population curve always follows behind the prey population curve, which makes sense. When the number of prey animals goes up, there will be more predators soon after, as they have more food. With more predators, the number of prey animals goes down again, and subsequently, the predator numbers will also dwindle due to a lack of food. Then the prey population can grow again. This can also be nicely seen in the phase portrait. Up left, down right, on and on and on. The second rule states that both populations fluctuate around a fixed average. This average is given by the stationary point we already looked at. This fact is easy to observe in the phase portrait. In the graph on the top, we can kinda see it if we add a running average for both curves. That these averages are in fact given by the stable solution to our differential equation is, however, a bit tricky to show. The third rule states that if we reduce both populations by the same relative amount, average of the prey animals will rise for a short time, while the average of the predators will fall. Which makes sense, as the predators rely on the prey animals, but we assumed that the prey animals themselves have basically infinite resources they can use. If we do reduce the number of animals in our simulation, we see this effect nicely in the population graph. In the phase portrait, it means that we teleport our point to the bottom left. It then starts to circle a point that's farther to the bottom right than the usual center. But that's difficult to see here. You probably can see how the first two rules can easily be observed in nature, but you might wonder how the third one could ever be. However, this reduction of both populations is what happens during wildfires and similar natural disasters. And that brings us to things that actually happen in the real world. While these rules can be observed, they rarely appear as nicely as I presented them. I already said several times throughout this video, these models are always simplifications. Best example for that is the dataset collected in the late 18th century in Canada. It tells us the population numbers of snowshoe hares and lynx. You can see the waves in the population numbers we talked about. Alas, the peaks of the lynx population come too early. In other words, the population point doesn't move counterclockwise in the phase portrait, but diagonally back and forth. Because it's almost the opposite way of how it should be, this is sometimes called the hare-eating lynx paradox. But other explanations are more likely. First, these numbers aren't population numbers. They are the number of pelts trappers collected for the Hudson Bay Company. But lynx pelts are more valuable than hare pelts. So, the trappers might not have hunted both populations at a similar rate and therefore influenced them asymmetrically. Other potential factors are changes in the weather and climate, other predators, or fluctuations of food resources of the snowshoe hares. And this is just one possible way to make the basic Lotka-Volterra model more accurate, incorporating additional information about the environment. Instead, we could also make the equations themselves more accurate, for example, by adding the intraspecies competition back in, which we studied in the chapter on logistic growth. This could go on and on and on. We could try to factor in more and more aspects of the habitat we are studying and compare each iteration of the model with the real-world data. For the Hudson Bay dataset, there are countless papers on this topic that try to incorporate any number of potential factors. But at this point, you probably can see how describing the rate of change of interconnected quantities may help to analyze the dynamic behavior of those quantities themselves. Even if that behavior is very complex, the differential equations governing it can be often much more manageable. So it's a good point to stop here and to thank you for watching. Until next time.